I'm Batyr Charyyev, PhD candidate from Stevens Institute of Technology, and today I would like to talk about our work on voice command fingerprinting with locality sensitive hashes. So let me start with the introduction. So as most probably all of you know, smart speakers like Amazon Alexa, Apple Siri, and Google Assistant become our digital helpers. They have central role in IoT ecosystems because they enable to control other IoT devices in the smart environment. For example, a user can change the thermostat degree to a certain degree by just giving the voice commands, and the smart speaker will change the thermostat degree or enable to control other IoT devices in the environment. However, privacy of the users using the smart home speakers are compromised. It's still a question. So for example, Amazon Alexa security bug allowed access to voice history of the users, or another user from the San Francisco reports that his smart home speaker started cheerfully saying, every time I close my eyes, all I see is people dying. Or another example might be a couple from the Germany. They received the voice recording of the another smart home speaker users, and which contained the public information like where do they live and their private conversations. So this list can be further extended, and in this study we are focusing on the fingerprinting the voice commands on smart home speakers. So when we look at the traffic patterns of the voice commands, we see that voice commands have different traffic patterns. For example, in these figures, we show that two different voice commands, each are repeated 4 times. For example, first one is what is the capital of Spain, and the other one is play national public radio. So if we just look at its traffic rates, we can see that similar voice commands have a similar traffic patterns, and the different voice commands have different traffic patterns, which enables to differentiate them and identify the voice commands by just looking at the traffic patterns of the smart home speaker. So in this paper, we focused on the fingerprinting the voice commands on the smart home speakers using our new technique, which doesn't require the feature selection or extraction from the data. So to do that, we used the data source from the study by Kennedy et al., which with the title of "I can hear your Alexa voice command." I can hear your Alexa voice command fingerprinting on smart home speakers. So in this study, authors tries to fingerprint the voice commands on smart home speakers using the website fingerprinting techniques. They collected traffic data of the 100 voice commands, and it was collected by 2 different students, each of them repeating each voice command 5 times. And this traffic data was collected on Amazon Echo 2nd generation, and the voice commands were selected based on the Amazon Echo service emails from August 2018 to November 2018. So in this study, we used their data set, and we evaluated our new approach. So basically, our new approach is based on the locality sensitive hashing of the traffic data. So locality sensitive hashing takes the data and generates the hash value, 32 bytes hash value, which we refer in the rest of the presentation as a signature. So this locality sensitive hashing is different from the cryptographic hashes. So in cryptographic hashes, as you know, a small change in the input produces entirely different outputs. However, locality sensitive hashing generates similar hash values for similar inputs. So we particularly used the nil SIMSA, which was proposed for spam detection. And so our motivation is, we say that similar voice commands have a higher hash similarity, and since we are taking the hash of the data, it enables us to fingerprint the voice commands without feature selection and the extraction, which is necessary for the machine learning techniques. So when we look at the hash similarity of the different voice commands, we see that different instances of the similar voice command, like play national public radio, for example, they have higher hash similarity compared to the other voice commands. And for example, voice commands which have a higher semantic similarity, like what is the weather and what is the weather for Sunday, also they have a higher hash similarity. So basically, this higher hash similarity between similar voice commands enables us to identify what was the voice command to the smartphone speakers. So let me talk about our approach that we're proposing. So first, we generate a set of signatures, a set of hashes for each voice commands using the nilsimsa hash. And then when we try to identify a new voice command, we again compute its hash value and compare to the set of hashes stored in the database, and basically return the voice command which has the highest hash similarity. So it's important to note that generating the initial signatures are done only once, so it doesn't have any future overheads. And if you want to integrate new voice data from the new voice command, we just append it to the end of the database. So let me talk about the evaluations. So we evaluated in terms of the precision and recall and accuracy. We also evaluated in terms of semantic similarity ranking. As we said, there might be voice commands which has higher semantic similarity. For example, if our model predicted as the voice command, what is the weather for Sunday? And if its actual label is what is the weather, we cannot say that the prediction is completely wrong. So to evaluate it, we use a semantic similarity ranking. So to do that, we use a dog-to-egg models, and these dog-to-egg models are trained on the Yahoo answer manner question dataset. So basically, we generate a vector representation for each voice command using the dog-to-egg model, and we compute their similarity using the cosine similarity. And for each voice command, we rank the remaining 99 voice commands based on their similarity, and the SSS semantic similarity ranking is the average rank of the predicted label for each voice command. So it's important to note that low semantic similarity ranking means higher semantic similarity between the actual and predicted labels. So let me continue with the evaluation. So first, we evaluate the two different locality sensitive hashes. One is a nilsimsa and the other one is TLSH. We observed that nilsimsa achieves higher accuracy in terms of the precision and recall and the semantic similarity ranking. And however, we observed that TLSH is more lightweight in terms of the processing speed, which is generating the hash of the network traffic flow, and hash size, and the response time, which is identification time of the voice command. So as I already mentioned, low SSS ranking means a higher semantic similarity. So basically, nilsimsa achieves higher accuracy. The evaluations, we continue to the results of the nilsimsa. We made a comparison to the previous study by Kennedy et al., which uses website fingerprinting techniques, and we made a comparison to the machine learning models. So for machine learning models, we gave features like duration and the ingoing, outgoing packets, and the packet size and interarrival time of the packets. So random prediction is average accuracy for random prediction is 1%, as there exist 100 different voice commands. And the average semantic similarity ranking is 49.5. So we made a comparison to the website fingerprinting technique. First table shows the comparison to website fingerprinting techniques. As you can see, our approach achieves accuracy and the lower semantic similarity ranking. So basically, fingerprinting with the nilsimsa achieves a higher accuracy compared to the previous study. And also in the second table, we can see that it achieves higher accuracy compared to the machine learning techniques. However, overall, the accuracy is not 99%, but it's nearly equal to 40%, which means that from 100 different voice commands, the attacker can identify using the nilsimsa hash 40 of them. So I think it's high enough. So, and we also evaluate the impact of the traffic pairing technique, which is specifically we use it to Buffalo and buffer fixed length obfuscation, which is the pads the network traffic to hide the unique traffic patterns that enables to identify the voice commands. So we observed that it significantly reduces the accuracy of our method and the other website fingerprinting techniques and machine learning models. However, we observed that each voice command on average produces around 900 kilobytes of additional communication overhead, which leads to the 17 seconds of the time delay. So on average, this technique, this padding technique reduces the accuracy of the fingerprinting methods. However, it requires additional communication overhead. So additional techniques needs to be explored, and we should come up with new methods to hide the network traffic patterns of so that it will disable, so that it will prevent fingerprinting the voice commands. So to conclude, in this paper, we focused on the fingerprinting voice commands on smartphone speakers, and we proposed a technique which doesn't require feature selection, and we observed it achieves a higher accuracy, and it achieves a comparable or better accuracy compared to the machine learning models. And we also evaluate the traffic padding technique to its impact on the fingerprinting accuracy of the fingerprinting methods. We observed that it can reduce accuracy significantly. However, it has additional costs, so new techniques should be developed. So this is the end of my presentation. If you have any questions, I will be happy to answer your questions. And thank you for listening, and thank you for your time.